Namaskar my dear friends. So let us design one IC which is 42 volt quad monolithic synchronous step down regulator. So this is a buck regulator kind of thing which is LT8602, and this can be used in your automotive cluster design power solutions for your processors or system on chips, that is SoCs. It can be also utilized in automotive infotainment or industrial control power supplies. So this is the IC that is of two variant. One is 40 pin variant and another one is 48 pin variant. Okay. So in our design, our client designs, we have taken 48 pin variants, and in this session we will try to understand what are the details and design techniques and guidelines. I will try to make sure that each and every steps of design process are very simple and very crisp. Okay. So let us get into the design and detail of this particular IC, which is synchronous step down regulator having quad monolithic. Quad monolithic means four outputs will be there. Okay. So there are four different voltage outputs that can be taken. So generally we have designed one of the application with 5 volt output, 3.3 volt output, 1.8 volt output and 1.2 volt output. Okay. Generally these are the voltage levels that are used in your processors or SoCs. There is a possibility of using 2.5 volt as well, so one of the voltage can be changed to 2.5 volt. Okay, good. So as we get into the this particular IC details, so this is a product page which gives you the understanding of what are the different features and capabilities of this particular IC from the analog devices website, and this is the datasheet link. So both the links I'll paste in the uploaded video. First of all, quickly we will try to understand what are the different maximum ratings that we should have. So the input voltage and power voltage input of channel 1 and 2 is minus 0.3 volt to 42 volt. Okay, so that you have to keep in mind. Okay, so up to 42 volt it can take up the input, and for channel 3 and 4 it can take up to 6 volt only. Just 6 volt will be the maximum input that can be taken. Okay, under voltage lockout and all we will not utilize, we will utilize just enable features. Okay, and we will be having a feedback pin which is having feedback 1 to 4, 1 2 3 4. Okay, similar to that we have power good option PG1 to 4. Okay, so their maximum voltage ratings are given here. It has three kinds of ICs. One is LT8602E, then I and J. Okay, so we'll be utilizing E series, which is going to be minus 40 degree centigrade to 125 degree centigrade. Okay, with this let's get into the features of this particular IC. So the features of this particular IC is it is very flexible power supply system providing four outputs with a wide input voltage range. So basically we are going to take input voltage around 12 volt. It can be taken up to 15 volt also, or 20 24 volt system as well. Okay, but I'll prefer to go ahead with 12 volt system. Now it has two high voltage synchronous buck regulators, so you can have there are four channels, so two channels will be having high voltage and rest two channels will be having little bit of lower voltage. Okay, and they can give you up to 2.5 ampere of current rating and 1.5 ampere current rating. Two low voltage current synchronous buck regulators are there, which is going to give you 2.6 volt to 5.5 volt input voltage range, and they can give you the output up to 1.8 amperes. Okay, it has a programmable switching frequency which can be programmed from 250 kilohertz to 2.2 megahertz. So we'll be generally working with close to 700 kilohertz or 1 megahertz. I'll tell you what is the advantage and disadvantage of utilizing higher frequency and lower frequency. As you go on higher switching frequency, your inductor size can go lower. So if you want to reduce the inductor size, okay, then you have to utilize switching frequency little bit higher. Okay, so this is how the L value will go lower. Good. We have low ripple burst mode operations. Okay, so there are two modes of operation. One is burst mode operation and another one is pulse skip mode operation. We have programmable power on reset. We have power good indicators. So power good indicators basically whether the output is in its a specified range or not. Okay, and it is AEC-Q100 qualified for automotive applications. So that's the main understanding. So this can be utilized in your automotive system, as I already mentioned in the first page itself, that it can be a very suitable candidate for your automotive cluster design systems, or like automotive infotainment systems. Okay, and it can be utilized in distributed power supply regulations as well as industrial control and power supply, where very high precision regulators are required. Okay, and generally this particular IC will be used for your processor power supply as well as your generally IOs power supplies. Okay, so what is the outcome of this particular session will be this. So this is the design, complete design that we have done. Okay, so we have the input voltage here with I will tell you each and every one, like how it is connected, how the capacitor will be connected to each and every pins, and we'll be having outputs as like 5 volt, 3.3 volt, 1.8 volt and 1.2 volt. Okay, and their current ratings will be also shown. It is actually shown here, like 5 volt is given as 1.5 volt, and 3.3 volt is 5 volt is of 1.5 ampere, then 3.3 volt is 0.8 ampere, 1.8 volt is 1.5 ampere, and 1.2 volt is 1.8 ampere. Okay, so anyway, this particular design we will try to understand later. First we will try to understand the design and details of this particular IC. Okay, so let's get into the typical application. So typical application, you can see very simple design. What you have to do simply is, you have the input voltage with a capacitor like decoupling capacitor, or we have the input voltage PV in 1, PV in 2, and then PV in 3 and PV in 4. There is 4 channel, 1, 2 and 3 and 4. Okay, and this input pin is for internal functionalities regulators. Okay, we have int VCC pin. Okay, and we have C power on, and then we have track soft tracking and smooth start. Okay, then we have RT pin, which is used for your frequency setting. We have sync mode, which can be utilized for your external clock signal. So if you do not want to utilize your switching frequency using this internal regulator, internal IC, then you can have a external switching, external frequency as well, external clock as well. And if you do not want to utilize, then you can either put it ground or put it high. I will tell you how to do that. Okay, very simply you can see SW pin and FB pins are used for your setting up your output voltage. So SW pin is your output, and FB pin is your setting the or regulating the output voltage. So using one inductor and two resistors, like let's say R1 and R2, so these two voltage divider resistors will be setting the output voltage to a value, particular value, and for current ratings you have to choose a particular inductor also. So those design process we will be explaining. Similar to that, other channels are also there, like channel 2, channel 3 and channel 4. This is very simple design using this particular typical application. Let me give you the IC specification or pin configuration. So we have 40 pin configuration, where 41st pin is actually the exposed pad, and similar to that we have 48 pin as well. Okay, so in this the pins are little outside, so that's the reason it has been used in our application. So we have preferred this particular IC, which is 48 lead LQFP package, and this is QFN package. So QFN package, the pins will be inside the IC, and LQFP package pins will be outside the ICs. Okay, if you talk about the ordering information, then we are going to have this particular IC, which is going to be LT8602 ELXE has PBF. Okay, so this is lead free finish. Okay, and this is 48 pin 7 mm cross 7 mm plastic ELQFP package, and the temperature range, as you can see, it has minus 40 degrees centigrade to 125 degrees centigrade. Good. If you want to utilize some other I mean part numbers, you can use that, but this is the part number that we have used in our design and application. So let me give you the design process very quickly. So what we'll do is, we'll try to understand each and every functional pins. So first of all, your job is to set the switching frequency using one RT, that is your resistor. So one resistor you have to put in your RT pin, and this is how you're going to set your a switching frequency that will be utilized. Okay, similar to that, we have channel 1 and channel 2. So there we will be having feedback 1 and feedback 2. So both the feedback pins are having 1 volt voltage. So you have to make sure that feedback voltage gets 1 volt, okay, and this is how you will be getting your V out. So this is my R1, this is my R2. Similar to that, for channel 3 and channel 4, same feedback pin will be set to 0.8 volt, okay. So you have to make sure this particular pin will be set to 0.8 volt, and this is how you will be calculating your values of R1 and R2 to set your V output. So this is how you are going to set your channel 1, channel 2, channel 3, channel 4 output voltages, whatever the voltage that you want to regulate, right? Now coming back to one bias pin. So one bias pin is there. So all these things are there, which is totally mixed up. So you do not want to spend a lot of time here, but this is going to be very simple when explaining like this, okay. So one bias pin is there. So bias pin, you have to connect it to greater than 3.1 volt, or let's say my output 2 is 3.3 volts, so you can connect it to that particular pin, okay. And all the ground pin and exposed pad, you have to connect it to PCB ground or the system ground that is utilized in your complete design. Let's get into the int VCC. So int VCC pin, what you have to do is you have to decouple with 4.7 microfarad capacitor to ground, okay. And what happens to this int VCC pin are basically, if your bias pin is connected to lower than 3.1 volt, then it will be 3.1 volt, okay. So this is kind of internal voltage regulator. So internal voltage regulator is going to give you an output of 3.3 volt, it is supposed to give you, okay. However, there is a variation because of the bias voltage input. So bias voltage is greater than 3.4 volt, then it will be limited to 3.4 volt. And if my bias voltage is between 3.1 volt to 3.4 volt, then the int VCC will be regulated to bias voltage equal to S, okay. Now we have power good operations. So power good indicators are like PG1 and PG2 for channel 1 and 2. So they are open drain pull up pins. So what you have to do is they will be pulled up only when the FB pin is regulated between 0.92 volt to 1.08 volt when my voltage output is rising, okay. So what happens, like I told you that FB pin was at 1 volt, so you can see it has a hysteresis of 0.16 volt total, right, up and down, like 0.08 volt down and 0.08 volt up, then also it will not give you the error, okay. And if below that it goes, then it will be pulled low. So this is how power good indicators are very useful to tell you that my output voltage is regulated at the desired output or not. Similar to that, we have channel 3 and channel 4 power good indicators, which is PG3 and PG4. So they are also open drain, and they will be pulled up when the FB pin is between 0.736 volt to 0.864 volts. So generally I told you that FB pin was at 0.8 volts, okay. So 0.8 volts, so here you can see that 0.064 volt up and down, it is going to give you the same indication. So this is how power good indicators are working. Coming back to power voltage input. So power voltage input for channel 1 and channel 2, so they can be powered up with different sources as well, okay. So like suppose you want to have power voltage at this point at 12 volt and this point at 15 volt, so no problem, both of them can be connected to different power supplies, okay. However, I will recommend you to connect both of them with a single source, because you do not want to have various power supply input in a particular system. And you have to bypass these two pins with a low ESR capacitor. So we will be utilizing let's say like 22 microfarad or 47 microfarad with 0.1 microfarad capacitors, that will tell you. Similar to that, we have channel 3 and channel 4 power inputs. So they can also be powered up with different sources, or otherwise they can also be powered up with the output of the channel 1 or channel 2, okay. So you can see one of the high voltage converters output that can be acting as a input to this particular channel, okay. So we have 4 channels, okay. So first 2 channels are high voltage converters, so one of them can be acting as a input to this particular channel 3 and channel 4, got it. And also they can be powered up with a different source, but the power rating the voltage output voltage input of these 2 pins must be less than 6 volt, okay. And we have reset B, so that is reset bar, which is power on reset output. Coming back to this SW pin, so as I already mentioned in the typical diagram itself, that SW pins are the like switch output where your inductors will be connected, and this is how you're going to get your output, and this is how the feedback will be designed. So this will be connected to your feedback, so R1, R2 and inductor. So this is your SW pin, and it is going to get connected to the corresponding feedback pin to set your output voltage. So similar to that, for channel 2 SW2, for channel 3 SW3 and channel 4 SW4 pins are given for your 4 outputs at the ICs. Okay, and we have sync pin. Sync pin is actually utilized for external clock signal, but suppose if you are not using external clock, then what you can do is you can connect it to ground. Okay, then it will be working as a burst mode regulator. Otherwise, if you connect it to high, that is, let's say 3.3 volt logic level, then it will be working in a pulse skip mode operation. So what we have done in our design is we have utilized burst mode operation, because we are using RT to generate my switching frequency internally. Okay, and we have a track soft start input, so that we are not utilizing in our design. And then we have V input pin. Okay, so input pin is actually input supply for various internal functions that are there that we will be using. Coming back to next one, so duty cycle. So duty cycle, as you can see, the IC is actually working based on some frequency, right, switching frequency. So it will generate some duty cycle. So that what happens is, if you want to find out what is minimum duty cycle, then that will be given as switching frequency into on time minimum. Okay, so Fs into T on minimum will give you the DC minimum or duty cycle minimum. And if you want to find out what is your DC maximum, then 1 minus this particular term will be giving you a duty cycle maximum. So I will suggest you, like based on the IC graphs and all, you can have minimum 0.2 to maximum 0.7 duty cycle, or 20% to 70% of duty cycle, that will be recommended. Okay, but this care must be taken. Okay, when you are going to utilize duty cycle more than 50%, because design will be changing a little. Okay, because at that time your inductor value matters. So generally it is recommended to keep your duty cycle less than 50%, so that you have proper design output. So as you can see from the graph also, let us say channel 1 peak current versus duty cycle. So you can see around 20% to going to around 70% based on the current that is there. Similar to that, channel 2 and channel 3 and 4 are there. So you can see channel 3 and 4 duty cycle is 30% to going up to around 80%. Okay. Okay, let us get into the block diagram of this particular IC. So what we'll do is we'll try to understand what this block diagram does. Okay, so very simply, as I'll tell you quickly, like power on reset, it is going to give you the power on reset output, then reset button is there, then input voltage is there, and which is going to give you the go to the regulator for various functionalities and various internal function regulators. Okay, and int VCC is there, which is coming as output also, which is going to give you equal to either bias voltage or 3.3 volt output. And internally there are a lot of references that has been generated, which you can see. This is 1 volt, 0.8 volt, and in VCC all the three are generated using your V input. Okay, coming back to RT and sync. So RT is actually used to generate your oscillator frequency, which is going to be FSW, that is switching frequency of the regulator, and this is going to generate a clock 1, clock 2 and SS3 and SS4. This can also be generated from your sync signal, which will be fed with some clock, external clock. Okay, so if you want to generate feed external clock, then you can utilize sync pin. Otherwise you can use RT pin to generate that oscillator frequencies. Okay, you have enable pin, and it can also be programmed for under voltage lockout. Then we have bias pin. Okay, and we have BST pin, that is going to be used for your PV in, and similar to that BST2 pin will be there for your PV in 2. Okay, so PV in 1 and PV in 2 both are having one separate BST pins, which is going to get connected through a capacitor to the PV in pin. Okay, Coming back to the channel 1 and channel 2, so channel 1 you can see there are two MOSFET, high side MOSFET and low side MOSFET, and they are going to generate your outputs to the SW1 pin, similar to that SW2 pin, and both will be giving you the output at SW1 and SW2 to your regulated power supply or regulated voltage output. Coming back to your FB pin, like feedback pin, so feedback pin, as you can see here, we are going to connect the feedback network through the resistor, and that will be going to generate some voltage level, and that is going to get go to the error amplifier, and this error amplifier will give you the I limit and all these voltage functionalities. Similar to that, you can see a power good operation. So this is going to come up at the output of your comparator. So comparator, you can see this is kind of schematic trigger, and as I mentioned, FB pin was set to 1 volt. So if it goes below 0.92, then it will give you error, or if it goes above 1.08, then also it will give you error. If it is between 0.92 to 1.08, then it will give you that it is having good indication, and it will give you a high in output. Okay. Similar to that, PG1, PG2 is also having the same functionality, and similar to this, like SW1, SW2, we have SW3 and SW4 also. Okay, so if you see SW3 and SW4, so what will happen? Let me just increase this and tell you. So what is going to happen? We have a power output 3 and power output 4, and we have same way feedback 3 and feedback 4 with their corresponding schematic trigger outputs with power good outputs. Okay, so this is a complete block diagram of your particular IC that we are having discussion here right now. Now let us get into the more designs. What we are going to do is the output voltage setting. So output voltage setting, as I already mentioned you, set the output voltage using the feedback resistor R1 R2 at your V output X. So V output X, let's say V output 1. Okay, so X means like 1 2 3 4, that is all these things, and LX means L1 L2 L3 L4. Okay, so what will happen is, suppose let's say R1 and R2 in R1 is equal to R2 into V out X by FB reference minus 1. So let us say my channel 1, my output is channel 1, my V out 1 is equal to 5 volts. So what will happen? I'll tell R1 is equal to, let us say R1 we are going to consider maximum value of R2 must be 200 kilo ohm, okay, or otherwise less than that. It should not be more than 200 kilo ohm. So let us say 200k I am going to use. So divided by what will happen? In 200k into V out, that is 5 volt, divided by feedback voltage, that is 1 for channel 1 and 2 and 0.8 for channel 3 and 4. So if you do this, then it is going to give you how much? 800 kilo ohm. Okay, so this is how you are going to set your output voltage of channel 1 using 800 kilo ohm and 200 kilo ohm, something like that. Okay, or otherwise you can reduce this value so that it will also reduce accordingly. Got it? Good. So this is how we have done this. Coming back to the switching frequency setting. So switching frequency setting, as I already mentioned you, we have the RT pin which is going to give you have a resistor. So if you want to set it to, let's say, 1 megahertz, then you can utilize 60.4 kilo ohm. Okay, and if you want to set it to 1.5 megahertz or 1.25 megahertz, then 47.6 kilo ohm will be the thing. If you want to calculate exact reading of this particular switching frequency, then you use this particular formula. So let us say if you want to calculate frequency, let's say Fs is equal to 700 kilohertz. So for 750 kilohertz it is given 81.2 kilo ohm, but if you want to use 700 kilohertz, then what will happen? 61.9 divided by 0.7 minus 0.009 minus 1.9, and this is how you are going to get your output value of your RT value to set the switching frequency to 700 kilohertz. Okay, so I'll recommend go by this particular table. That is more than enough. You don't try to do R&D of different values. Okay, or otherwise it's up to you like how you're going to do that. Now coming back to the voltage range input. So V in range, V in must be greater than 3 volts so that it can like give you the int VCC and internal functional voltages on all those things. Okay. So simple design, if you want to do, what you can do is all these V input, PV in 1 and PV in 2, all these three you can connect together and with one power supply, which is going to be, let us say, 12 volt or 15 volt of your system. Okay. And we have run 3, run 4, which will be the run input for the low voltage converters, which is channel 2 and channel 3. Okay. Coming back to the PV in ranges. Okay, so PV in ranges, like power voltage input range will be for channel 1 and channel 2 it can go up to 3 volt to 42 volt, and for channel 3 and 4 it will be going to 2.6 to 5.5 volt. Okay, so you have to make sure that 2.6 volt to 5.5 volt is the input for channel 3 and channel 4, and it can go up to 42 volt for channel 1 and 2. Now there are limitations. Let us say you have some specific value of V output. So based on that, what will happen is your power voltage input maximum and minimum values depends on your duty cycle maximum and minimum. Okay, so power voltage input minimum will be V output X divided by DC max. Okay, so what will happen is, let me give you an example. uh, let us say we have the power voltage output as 5 volt and we have DC maximum as 50%. So what will be the minimum input that will be required to get this particular output is PV input minimum will be 5 divided by 50%, that is 10 volt. So the input voltage will be at PV in 1 must be 10 volt or more. Okay. Similar to that, let us say DC minimum is 20%. In that case, PV in minimum will be for this particular situation is what? 5 by 20, that is going to be 5 by 0.2, that is going to be 25 volt. So my PV in range is going to be 10 volt to 25 volt. Okay. So this is how you generally define what would be your system input at each and every channel. Similar to that, for other outputs and other DC maximum and minimum values based on your decisions, you can utilize that and try to find out what is the PV input ranges. So generally, if you take DC maximum 70%, then what will happen? Even PV in minimum will reduce, right? So if my duty cycle is increasing, my PV in range will start reducing. Okay, PV in value will start reducing, the minimum requirement will reduce. Coming back to the most important part, which is going to be inductor selection. So in the inductor selection, what is the thing is, like Lx is going to be Kx into V out X by PV in X multiplied by PV in X minus V out X by Fs. Okay, so what is going to happen is, X means the channel number. Okay, so let us say we want to channel number 1, what will be the thing? So you want to find out, so what is the value of L1? So L1 will be K1. So K1 is nothing but 1.6 that you have to utilize. K2 is 1, K3 and K4 is 1.3. Understood? And let us say we want to utilize, let me give you an example directly. So this particular formula we will be using to find the inductor selection for your particular V output that is required, right? So if I take an example, let us say we have V output as 5 volt and we have V input as 12 volt. So this is output. Let me give you V output is equal to 5 volt and PV in 1 is going to be, let's say, 12 volt and Fs is going to be 1 megahertz. Okay, so in that case what will happen? My L1 value will be K1, that is 1.6 multiplied by 5 divided by 12 into 12 minus 5 by 1. So that is going to give you around 4.66 microhenry. Okay, so generally this is a good starting point of your inductor value. Okay, now suppose you always try to utilize little bit higher side, so I am going to use for the same part 6.8 microhenry. Okay, and what is the a ripple current that will be utilized? So ripple current will be actually the current that is going to be above this, right? So this formula we will be using for that, which is going to be V out X by Lx into Fs multiplied by 1 minus V out X by PV in X maximum. Okay, so what will happen is 5 divided by 6.8 multiplied by 1 minus 5 by Suppose you are like having PV input maximum little bit higher than 12, right? So you can utilize 15. So this is how your delta L will increase. Okay, so delta IL will increase a little bit higher. So in that case, right now I have 1.43 ampere, and what would be my let's just say my output maximum is 1.5 ampere for that particular channel. So the total peak current that will be seen at the inductor will be 1.5, that is I output maximum plus ripple current by 2, so that is going to be 1.71 ampere. So you have to make sure your inductor rating in inductor current rating is more than 1.7 amperes. That's the reason you can take it either 2 times or like 3 times current of this particular calculation. So this is how you will be selecting your inductor based on the values and the current ratings or saturation current ratings. The very good thing that the manufacturer has done in the data sheet is they have given the vendors like TDK, Sumada, Coilcraft, NIC, or Worth Electronics. Okay, so generally I prefer like Coilcraft inductors or maybe Worth Electronics also. So Worth Electronics part and like Coilcraft part, I'll give you the part numbers for our designs. Okay. Any other vendors are also the same, like you can utilize those particular inductors from all other companies as well. Even Panasonic and Kemet produces lot of inductors. Even Murata produces lot of inductors. Murata Electronics, and what is that? Panasonic. Then I told you Kemet, and even we have Burns. Okay. So all these like companies are also a good manufacturer of different fixed inductors. Okay. So we saw one of the selections similar to that for other inductor values, for other like outputs like 3.3 volt or like 1.8 volt or 1.2 volt. You can put down the values, put down the all the input voltage and output voltage that is required based on the frequency. It will give you the particular inductor values. Okay, so this is very simple design. So I am giving you the indication how to design it very quickly. Got it? Coming back to the output capacitor selections, output capacitor, what you have to do is you have to C out must be greater than or equal to 10 times the inductor value that you are going to have, and then I limit by V output, and this is how you will be selecting your inductor also. Capacitor also. So generally capacitor you try to keep higher than the like calculated values, that is better. Good. So this is how we have like done this complete design. Now what we'll do is like you can like see this particular PCB layout, like one of the layout engineer that will be designing your particular circuit, so he must like refer this particular layout guidelines so that he designs the particular output properly. This particular PCB layout guidelines actually helps all the layout engineers as well as designers to make sure that where will be the output like 1, 2, 3 and 4, and how my inductor should be placed so that it has a very minimal like effect on other things, and you have to make sure the feedback lines must be away from the inductor lines. Okay, so inductor noise may like uh, I mean give you some problem at the feedback lines. Okay. Good. So alright guys, what we'll do is we will try to see one of the application right now which is given in the data sheet itself. So let us say the data sheet has mentioned 6 to 42 volt. So I am going to take input as 12 volt, and the output that is mentioned here is like 5 volt, 1.5 ampere, 3.3 volt, 0.8 ampere, and 1.8 volt, 1.7 ampere, and 1.2 volt with 1.8 ampere ratings. Okay. So same design actually we have used in one of our application for our automotive cluster design for the processor power supply. So this particular design we will be utilizing in our design process. Okay. So what we will do is directly we will get into the design method here. So in this particular design, what we had done is these are the three 22 microfarad capacitor, and according to that we have 0.1 microfarad capacitor also. So each of the 22 microfarad plus 0.1 microfarad should be at V input. Then these two will go to PV1, PV input 1 and then PV input 2. So PV input 1 2 pins are there, and PV input 2 also 2 pins are there. Okay, so you have to make sure that each of the 3 pairs will go to each of the 3 pins. Got it? And for simplicity, I have utilized enable pin directly to the V input, so there is no need of like under voltage lockout design or something like that. So this was all about the input power supply. Got it? Coming back to the like ground pin that is connected, so ground pin is fine. Then set your frequency setting. So frequency setting, I have set it 60.4 kilohertz, so it is going to give you 1 megahertz like switching frequency. Got it? Then we have like a track and soft. So this is going to give you 2.2 nanofarad. It is directly grounded. Okay, coming back to int VCC, so int VCC has been grounded with 4.7 microfarad, and I do not want to use sync pin and power enable pin, so they have been like grounded, and pad is also grounded, right? So this is our basic design. Coming back to our run mode, so run mode has been utilized directly with like 3.3 volt, one of the output that was there here. Okay, and all the PG pin, that is power good output pin, has been designed with had been pull up, and they will go to my microcontroller GPIOs. So microcontroller GPIOs will make sure to give you an understanding like whether the outputs are in their specified range or not. Okay, now coming back to the design of output voltage ratings. So output voltage ratings, what I am going to do is, let us say for 5 volt output, what I am going to do is, the L1 value is 6.8 microhenry, and with this feed forward capacitor which is 10 picofarad, and this is the R1 and R3 which is going to design the feedback resistor network, which is 453 kilo ohm and 113 kilo ohm. So this 113 kilo ohm, 453 kilo ohm, this is going to give you the output of 5 volt at the channel 1. Okay, so switch 1 channel 1 is going to be designed with this particular 3 values, which is R1, R3 and L1. Okay, now coming back to channel 2, so channel 2 also we have L1 value, L2 value as 2.2 microhenry with R4 and R5 which is 316 kilo ohm and 137 kilo ohm. This is given in the data sheet as well directly, so I have not changed the values. If you want to change, then you have to utilize the formula of feedback resistor network to have a different values of resistor. Okay, similar to that for channel 3 and channel 4, what I have done is, channel 3 and channel 4, the power inputs, that will be PV in 3 and PV in 4. So that I am going to utilize channel 2 output. Okay, so channel 2 output is 3v3, that only will be utilized here, and each of them have been decoupled with 0.1 microfarad and 10 microfarad capacitor. So PV in 3, you have to put one of the 10 microfarad and 0.1 microfarad capacitor. Similar to that, PV in 4, you have to put 10 microfarad and 1.1 microfarad capacitor. Okay, and if you want to utilize separately, then you can utilize separately, but this is the good way of designing the circuit entry. The bias point will also get connected directly to this, so that it also get biased to 3.3 volt. Okay, now coming back to the resistor divider network. So resistor divider network, it has been used 200 kilo ohm and 249 kilo ohm to give you the output of 1.8 volt, and based on the current ratings and all, the L value that is L3, which has been designed to 2.2 microhenry. Similar to that, channel 4 is going to give you 1.2 volt output, which will be designed with L4 value as 1.8 microhenry, and R8 and R9 is the feedback network, which is 100 kilo ohm and 200 kilo ohm to give you the output of 1.2 volt. Okay, and all of them have been utilized like capacitor with like 22 microfarad. So I have given the provision of 1206 package, so it can be utilized even higher values, let's say 47 microfarad each one of them. Okay, so based on the load, you can increase the value of this capacitor to 47 microfarad, so that you do not land up into any problematic situation. Okay, and all these capacitor must be a very high end capacitor of like a ceramic capacitor, or like ceramic polymer capacitor. So this ceramic polymer capacitor can be always found out from like Panasonic. So Panasonic is one of the very good capacitor manufacturer for this, or like you can utilize TDK or Camet, Okay, even AVX Yageo is also there. Okay, Yageo is there. Then we have Samsung Electromechanics. Okay, but for this particular capacitor you go ahead with Panasonic, TDK and Kemet. That will be better. Okay, and voltage rating you keep for 5 volt, you keep voltage rating like 10 volt or more than 10 volt, like let's say 16 volt. Okay, so up to 16 volt you can go ahead. For 3.3 volt you can go ahead up to 10 volt rating, and for 1.8 volt you can go up to as minimum as 6 volt also, or more than that even 10 volt will do, but 6 volt should be minimum. For 1.2 volt also 6 volt rating should be minimum. Okay, not less than 6 volt. Or okay, or even 4 volt you can go ahead at the extreme phase, you can go ahead with 4 volt rating of capacitor, but recommendation will be close to 6 volt or even 10 volt. Okay, however all the 0.1 microfarad capacitor you can always go ahead with 25 volt rating or 50 volt rating for all 0.1 microfarad capacitor. Understood? Good. So this was the complete design of this particular application that we had in our hand. And coming back to the inductor selection, so inductor selection I have given you a table of this particular inductors from Coilcraft. So Coilcraft, this was also suggested in data sheets. Okay, so XAL5030 series is there. So based on the any values of inductance, let us say our values were 1.2 microhenry and 2.2 microhenry, then we had 6.8 microhenry, and what other values were there? 6.8, 2.2, 2.2 and 1.8. Okay, so these three values you can take. 1.8 is there. Okay, wait a moment, we have 1.8 microhenries, 1.8 is not there. Okay, you can, if you want, you can utilize 2.2 for all the three below outputs, so that is more than enough. Okay, and you can see it has a good IRMS also. So saturation current is up to around 6 ampere and the requirement was just 1.7 ampere, right? So it is good. Coming back to another vendor of inductor selections, I have taken from Worth Electronics. If you go ahead with Worth Electronics and type it WE-PDF, so PDF is the series of this particular conductors. Okay, so SMT power inductors or similar to that, SPC is the series, and SMT is the series. So these three series you can utilize your particular values that is required. Okay, so I will suggest you to go ahead with Worth Electronics. They will be having better capacity and better inductors with low cost as well. So alright guys, if you do have any other questions regarding this particular implementation, or if you do want to have the other outputs, and based on that you want to design a particular resistor feedback networks for different output voltages, then you can put down your queries in the comment box. Or if you do have any particular processor which requires a particular voltage supply, let us say 2.5 volt or 1 volt, and generally I'll just give you an example that automotive cluster design. So a lot of SoCs or processors are being used. So they require let us say 0.75 volt or 0.85 volt core voltages, and then 1 volt will be there or 1.2 volt will be there. So they as low as 1 volt or 1.2 volt, and this 0.75 volt and 0.85 volt. So for this you can utilize lot of other power supply that we have already, and similar to that this also you can utilize. So in our previous session also we have given you the power supply design for FPGA, so that can also be utilized for your power supply design. However, this is one of the best method or best choice for your automotive processor power supply designs. So alright, if you do enjoy this, then like and subscribe our channel. Thank you so much.